Hi everyone. In this video, I'm going to talk about integration. What does this symbol mean? What are the equivalent classical operators of this symbol? Why do we need dx or something like this? Okay, I'm going to start with a classical problem. It is the sum of numbers between 0, for example, and 10. Okay, what is the sum of 0 plus 1 plus 2 plus 3 and plus 8 plus 9 plus 10? Okay, what's this equal to? I'm going to use the sigma notation to find a formula for this problem. Sigma from n equals 0 to capital N. Okay, any other number, 10 or any other number for n. We expand this 0 plus 1 plus 2 plus 3 plus other terms until plus n minus 1 plus n. Okay, I write this expression, but I'll expand this summation backwards, starting from n. Okay, we have n plus n minus 1 plus n minus 2 plus other points plus 2 plus 1. Okay, now by adding these two equations, what do we get? Okay, 2 times the summation and what do we have here? We have 1 plus n. 2 plus n minus 1 is again 1 plus n. 3 plus n minus 2 is also 1 plus n, and so on. Here we have n minus 1 plus 2 is 1 plus n, and we have again 1 plus n. So the result of this summation is n times n plus 1. You know, these terms are n terms, starting from 1 ending with n terms. And we get n plus 1 each time we add a term from this equation to this. So n times n plus 1. Okay, the result of the summation, don't forget this too, will be summation from n equals 0 to n for n will be n times n plus 1 over 2. Okay, now we want to complicate the problem a bit. We actually want to find the sum between 2 points, 0 for example and 10, but using a step of 0.5. So what's the sum of 0 plus 0.5 plus 1.5 plus 2 plus other points plus 9.5 plus 10? We see the problem here is that this operator only works in an integer steps, actually in a unity steps. So we are going to modify this formula to force it to work in a step of 0.5 or any other step. Okay, we write summation from n equals 0 for 0.5n to 10, for example. Okay, what we have here is actually n will continue to work in an integer steps from 0 to 10, but effectively this term will move in a steps of 0.5. We will expand this summation, we get 0 plus, when n equals 1, this is 0.5 only. When n equals 1, this is 1. When n equals 2, this is 1. When n equals 3, this is 1.5. So we force the summation to work in a step of 0.5. The problem is, the last term will be, when n equals 10, 10 multiplied by 0.5 will be 5. So we get here 4.5 plus 5 is the last term. We want it to be 10. So another modification to solve this problem will be as follows. Okay, we write summation from n equals 0 to 20 instead of 10, 4.5n. Okay, this will start from 0 and will end with 10 plus 9.5 plus 10. That's what we want. Actually, this 20, we got it from 10 divided by the step we used, which is 0.5. So when n equals to this value, which is 20, it will be multiplied by this 0.5, and effectively this value will be only 10, which is the last term. Okay, so in general, we write summation for n equals, from n equals 0 to n divided by the step for n multiplied by the step. This formula, this expression, okay, we'll find the sum between any 2 points, actually from n equals 0 and capital N, okay, in a step of s. We earlier got that the summation from n equals 0 to capital N was n times n plus 1 over 2. So using this formula, we'll find the sum. We will get summation from n equals 0 to n over s for n multiplied by s will be. We have instead of n as upper term, we have n over s. So n over s multiplied by n over s plus 1 over 2. And don't forget this s, so times s. Okay, let me simplify this. This s will be n squared over 2s plus n over 2. Okay, so we have a formula for our problem. Don't forget that we want actually the sum until n. Okay, so upper limit is effectively n, not n over s. Okay, you should keep this in mind. Okay, what we are going to do now is to investigate this formula for small values of s. For example, the sum between 0 and 10 in a step of 0.01. So you substitute n equals to 10 and s of 0.01, and you'll sure get a very large number. So the smaller s, the larger the sum. For s approaches 0, this sum actually will tend to infinity. Okay, the sum will tend to infinity. We don't even need this formula to know that. I can get infinity by just adding the numbers between 0 and 0.1 only, by using a step that approaches 0. So everyone can do that. So it's not an achievement. It doesn't have any physical meaning as well. It doesn't have an application. It's useless. To make this formula useful, I'll do another modification on it. We put n over s and by s, the summation, we multiply it by the step we used. Okay? So what we get? N squared over 2s plus n over 2 multiplied by the step we used to evaluate this sum. Okay? And the result will be n squared over 2 plus n times s over 2. Okay? What's the physical meaning of this? We see if we add the numbers between 5 and 6, for example. Okay, so we have 5 in a very small step. 5, 5.01, 5.02, 5.03, and so on until 6. So we have 5 plus 5.01 plus 5.02. This is 5, this is 5.01, this is 5.02, plus 6. Okay, if we multiply this sum by the step we use, which is 0.01, okay, we will get the area of this shape. It's a trapezoidal. Okay, so this 0.01 will be distributed over all terms, so you get this magnitude 5 multiplied by this step 0.01. Okay, you get this area, and here we have another 0.01 multiplied by 5.01, and so on. You are summing the areas of these small rectangles, okay, until the last one, and you will get the exact area of this shape. Okay, so it does have an application. It's finding area under a curve. That's the advantage of multiplying by s. If we multiply the sum by the small step we used in finding this sum, we get the area of a shape. Okay, of a function in general. The function in this case was x. We'll get there. Okay, so we will put s approaches 0 in a new formula and see what we get. So we have limit s approaches 0 for summation n equals 0 to n over s. Don't forget that the last term in the sum is effectively n, although that the upper term is n over s, since this n equals n over s will be multiplied by s over here, n times s, so this s will be cancelled. Okay, this, and we don't forget the other s right here. We get limit s approaches 0 for n squared over 2 plus n times s over 2 as we did earlier. Okay, we said that this will be area and a curve, so it has a physical meaning. Area. Okay, so if s is very, very, very small, this term will be cancelled, and the result will be only n squared over 2. Okay, so apparently we need a new formula, a new operator, since this becomes very complex. we have the issue of the upper term and the upper limit of this operator. It's different from the last term in the summation. Okay, we will define the symbol of integration. Okay, we will put, let me write s as dx. Okay, the summation, I'll replace it by integration. Okay, actually, not only the upper term will need a modification to make the last term n. Actually, the lower term also need to be divided by s, but since it was 0, so 0 over s will be 0, and we didn't notice this thing. You can check it later. Okay, we have n times s. I will write it as x. I'll explain that later. And to illustrate the effective limits of this operation, and it was 0 and n, not 0 and over s and n over s, I'll write n times s. So we have, if n equals n over s, so n over n times s equals n, and n times s equals 0. n times s I've earlier divided as x, so integration from x equals 0 to x equals n. Okay, if that's not so clear, we have summation from n equals 0 over s to n equals n over s. I have earlier divided that n times s equals to x. Okay, so n times s equals 0, ns equals 0, and here n times x, if n equals n over s, then n times s equals n. Okay, and we have integration from x equals 0 to x equals n. Now, how did the n times s became x? Okay, here we need to define the difference or the relation between the continuous variable and a discrete variable. What's the difference between n and x? n is a discrete variable. Okay, it takes values 0, 1, 2, and so on, while x is a continuous variable. It takes any value starting from 0, for example 0.0001, 0.0002, 0.0003, and so on until 1, then 1.0001, 1.002, and so on. It can take any value. So what's the relation between these two parameters, these two variables? You can see that we have here 0, 1, 2. We also have here 0, 1, 2, 3. It also counts in the same way, 1, 2, 3. The only difference is that it's multiplied by a very small number. So we can say that the x, which is the continuous variable, is the same as a discrete variable like n, but it's multiplied by a very small number, say dx. Okay? So this is the relation between a continuous variable and a discrete variable, which what we used when we replaced the n times s by an x. Okay? So as a summary, what we did earlier is that we defined a new symbol. Okay, we replaced a limit s approaches 0 for summation from n equals 0 over s to n equals n over s for n times s again. Okay, we rewrite it as, we define a new operator, which is the integration. Okay, now this operator doesn't work with n. It works with a continuous variable like x. We agreed that x equals n times s. So to start from the same point as this summation, the summation starts from n equals 0 over s. That is equivalent when x starts from 0. Okay, and ends with n equals n over s. That is equivalent to when x equals n. Okay, for a function which is n over s in this case, n times s, which is x, and this small number again, we said it's dx. So in general, we can find the area for a function, not only x, any other function. We have integration for f of x, starting from x equals a, any starting point, and ending with x equals b for f of x times dx. This multiplication by this very small number will make this very large number converges into area under f of x. Okay, one might say, how do we find the area under the rectangle, actually the trapezoidal, this is our function x, from 5 to 6 only? We want to find only this area, while our derivation was based on finding the sum from 0. So to solve this, what we do is find the area from 0 to 6, okay, this is 6, and also find the area from 0 to 5, and subtract the two areas, okay? So we get the area required. So if we define integration for f of x, this is an indefinite integral, okay? Say that the result is g of x. It's defined as the area of f of x from 0 to, okay, to x, any other number. So if you find it from a to b only, you find the area from 0 to x to b and subtract it from the area enclosed by 0 and a, and you got the area from a to b, okay? So that's what we mean when we write a definite integral and then substitute the limits of integration. Okay, this is g of b minus g of a. This is the area under f of x from a to b. Okay, I'm finishing this by telling you how do people understand the integration these days. Okay, people see that this thing is used to tell them what's the index of this operator. You see, in summation, if we write summation k plus n, now people ask you about the index of this operator, whether it is from n equals 0 or whether it is from k equals 0 to find out the index of this operator from here. Well, integration, they instead of writing integration over x, integration over y to find out the index of this operator, they use this. It wasn't actually invented for this purpose, but people use it anyway for this purpose. If you write integration x times y, okay, so if it's dx, we get y outside this integration, okay, since it's a constant with respect to this integration, and the result will be y times x squared over 2. And if you integrate x times y dy, then x will be a constant with respect to this integration, and the result will be x times y squared over 2. Originally, you should write the index of integration over here. You should write y, x. That's the original thing. It's not dy wasn't found for this purpose. The other thing is, people are using this thing and this thing as brackets to enclose the terms that are under the effect of this operation. For example, if you write summation n plus 1, so how to find out if this plus 1 term is under the effect of this summation or not? You write n plus 1 between two brackets to know that they are both under the summation effect. And if you're willing to extract it outside the summation effect, you write summation of n, okay, you write plus 1 outside these brackets, okay, or you write it right here, plus 1. In integration, what people do is this. If you write integration x dx, okay, people tell you that the result is x squared over 2. While if you write integration dx times x, okay, what people see that we have here 1, okay, they see that x is outside the effect of this integration, and the result of this integration is x. Okay, we have here x, the result is x squared. Okay, they use this thing and this thing as a bracket to enclose the terms that are under the effects of this operation. Okay, while it's definitely x times dx equals to dx times x. Okay, it's just a typical multiplication. I will end with this one. If we write integration x dt, let us assume that dt equals to 2dx, okay? People will tell you that x is a constant and the result will be x times t. Now if you force them to integrate over x, now they will tell you how this integration index is x, while this thing is dd, is supposed to be dx. So what I'm proposing is that the result will be x times dd over x squared, times dd over 2 dx. Okay, this dd is just a constant, and the result of integration under x will be x squared over 2 dx. Okay, if you substitute dd equals to 2 dx, the result will be x squared. Okay, so I know I'm starting a big argument over here, so I'm waiting for your comments on this video. Do you think that integration x without a dx equals to x squared over 2dx? Okay, that's it. Thanks for watching.